So I want to go over how to crack the linear feedback shift register. This is not easy, and it's not super algorithmic either, but let's just go through a couple of examples from the homework. So here's the first problem from our web work. And so you can see, in this case, you get to see a bunch of the output bits. And you have to find the initial state and also the tap bits. So I work this on a sheet over here. So here's the here are the state. Oh, sorry, these are the output bits. And from the output bits, you can construct the initial state. So if you set this up the way we typically draw an LFSR, let me just remind you, so. This is a 6-state machine. So the initial state of the machine would be S0, S1, S2, S3, S4, and S5. So if you'll notice here, that's what I've written here, is I've just copied those values in that order. And now coming out of these, we have wires. And these wires are multiplied times the feedback coefficients or tap bits. I consider those terms to be synonymous. So depending on whether or not the corresponding tap bit is 0 or 1, this is multiplication here, all these wires come up here and they get XOR'd together, and that is what produces the new input here. So what I've done in this matrix is I set up the initial state and then I just let the machine run. We don't know the tap bits, so we can't evaluate this new input, but we don't need to because it's given to us on this list. So rather than computing the next bit, we just take it from the list here because it's written down. So everything chunks over, the next bit is 0, everything chunks over, the next bit is 1, everything chunks over, the next bit is 0, etc. So that's where these come from. This is a 6x6 matrix, and so it represents 6 equations and 6 unknowns. So here I just translate from the matrix to the equations. So you'll see everywhere there's a 1, I put a corresponding p. These are the association between the indexes are given here. And over here we have, in this column, these are the output bits. Not the output bits, sorry. These are the new variable that's going to come back here on the left. So these are kind of equalities. If you perform the LFSR operation on these bits, then these are the outputs. So these are our 6 equations and 6 unknowns. So there's an algorithm for solving a system of linear equations that works mod 2 as well as in the real numbers, and it's called Gaussian Elimination. If you prefer to do Gaussian elimination, you can do that. It's just, that's an entire lecture unto itself. So I thought it might be easier just to solve this by tooling around. So the first thing I did is I noticed that if I add equation 3 and equation 5, everything cancels out except for P2. You'll notice that if you add a variable to itself here, if you add one of these coefficients to itself, then it doubles, but we're working mod 2. So anything that is doubled is canceled. So P2 is equal to 1, and then I go through and tool around a little bit more. I add equation 2 to equation 5. That gives me this. And then I make this substitution for P2, which puts a 1 over here. And now I apply this to equation 1. So I take these 3 variables and replace them in equation 1 with 1. And that gives me P3 plus P2. Plus 1 is equal to 0, but P2 is known, so P3 is 0. And so we know 2 variables now. Now, keeping on, write down equation 3, but with the known things taken out. So P3 and P2 are both known, so we can just replace those with the constants that they are. And if you add these 2 equations, then you get P1 plus P4 equals 0. This implies that P1 equals P4. Yeah, P1 equals P4. So now I apply this relationship to E4. So P1 and P4 cancel each other out. You get P2 plus P0. and P2 plus P0 is seen to be equal to 1. But P2 is 1, so that means P0 is 0. And now you can try to go further, but what you'll find, so I tool around a little bit more. So, you know, I get a couple of equations, like this equation tells you that if you put everything we've done so far together with equation 6, you can see that P5 and P4 are opposites, and P4 and P1 are identical. But then you run into a problem, which is every equation that has P5 also has either P4 or P1, which are the same. And nothing has just P4 or just P1, and not P5. So what we have here is this is a system of linear equations with well, in the real numbers there would be infinitely many solutions, but this is mod 2, so there's just a non-unique solution. So there's multiple solutions. In this situation, which hopefully doesn't happen to you, you end up with a free choice. So there are 2 choices you can make. These are the remaining unknowns at this point, P5, P4, and P1. So we can make a free choice that P5 is equal to 0. Then P4 has to be its opposite because of this equation, and then P1 has to be identical because of this equation. So that determines one solution, which is 0, 1, 0, 1, 1, 0. And you could have chosen P5 to be equal to 1, in which case P4 has to be the opposite and P1 has to be identical to P4. So that gives another solution, 100, 100. So if I type either one of those, I just got kind of paranoid that I wasn't recording, sorry. If I type either one of those into here, let's just try 100, 100. That works, and what was the other solution? The other solution was 0, 1, 0, 1, 10. Whoops. Whoop. 0, 1, 0, 1, 10. Okay. So both of those work, and the initial state is not hard. It's just you can actually read it right off here, right? You just have to go backwards. So I would take these 6 bits on the left and then just write them down in reverse order. So that would be 1, 1, 1, 1, 0, 1. Okay, and that problem would be done. So you also have to do problem 7. Problem 7 is arguably easier because you're solving a 4-state machine instead of a 6-state machine. This one has a little bit of, it's framed as a known plain text attack. So you don't actually directly get the key stream here. You have to figure out the key stream first. So the key stream is just the XOR of the known plain text and the observed ciphertext. Everybody gets to see the ciphertext. So if you XOR these things, what you'll find is that you get 0, 0, 1, 0, 0, 1, 1, 0. 0, 0, 1, 0, 0, 1, 1, 0, that's my key stream. So that means S0 is 0, S1 is 0, S2 is 1, S3 is 0, S4 is 0, and S5 is 1, and S6 is 1, and S7 is 0. So these are the outputs of my machine. So I can do basically what I did last time. I need to set up a bunch of equations. So the equations in this case, I take the initial state of the machine, take these first 4 bits, and then write them backwards. And so I get 0, 1, 0, 0. Okay, this is just the initial state of the machine. And the output in that case was S4, right? So this was equal to, sort of yields, S4, which is 0. Now everything clunks over. I can do all my clunks at once if I want to. So it's like this. And this 0 comes here. And so I can fill in these. So when the state of the machine was this, I got a 1. I got, right? Yeah, I got a 1. So a 1 comes here. And then finally, this yielded a 1 also. So I write a 1 here. and this yielded the final 0. So I have these, this is the matrix, and now I can translate that into equations just by remembering the association between the indexes. Okay, and so what this is saying is that P2 is equal to 0. So you get that one right off the bat. So P2 is just equal to 0. This one tells you that P1 is just equal to 1. And now from this last equation here, you can see that P3 plus P2 is equal to 0 from this last equation. But P2 is 0, so that means P3 is 0. And if P3 is 0, then P0 is 1 because of this equation. And you're done. So the solution is 0, 0, 1, 1. Is that right? Let's just check with the solution. Yes, okay. All right, so I'll do that. So it's 0, 0, 1, 1, check answers, done. Okay, so I'm gonna stop this and